This is Professor Ernest Rutherford and his assistant Dr. Hans Geiger. They were doing further research on alpha particles at the University of Manchester, where they recruited the help of Ernest Marsden, an undergraduate studying under Geiger, for a series of experiments. They didn't know at the time, but the three would notably contribute to the development of the atomic theory.
1908. Professor Rutherford wanted to find out more about alpha particles, but first he needed a way to individually count the particles. Alpha particles cannot be seen, but they can be detected. Enter the phosphorescent screen. He found that whenever an alpha particle struck a screen covered in zinc sulfide, it produced a visible flash which allowed them to track the paths of the particles. He performed an experiment where he used a glass tube of radium bromide as an alpha particle emitter and directed the particles to hit the aforementioned phosphorescent screen. By means of a microscope, he and his assistant would sit there and try to count the flashes of light going off.
The 1908 paper Dr. Geiger published details this very experiment. There is one line in it which had changed the trajectory of science forever. It will be noticed that some of the alpha particles were deflected through a quite appreciable angle. What? This intrigued the two physicists because according to what they knew about the atom at the time, it could not be explained.
This is J.J. Thomson's model. This was the most accepted model of the atom at the time. It depicts the atom as a positively charged sphere with negatively charged electrons embedded like raisins in a pudding. Based on this model, if a particle were to be shot straight at an atom, it would go straight through. Since there was an equal amount of positive and negative force throughout the atom, it wouldn't experience any force. But that didn't happen in the experiment. The physicists deduced that the only possible explanation of this was that there was a centralized charge in the center of the atom that was causing the alpha particles to deflect. It had to be positive because alpha particles were positively charged and like charges repel.
This breakthrough would lead to a series of experiments that modern physicists have simplified into the gold foil experiment that is known today. The Geiger-Marsden experiment is named after Hans Geiger and Ernest Marsden, who performed the experiment under the direction of Ernest Rutherford.
This is a simplified diagram of the experimental setup, but here's the apparatus that was actually used. Here the zinc sulfide screen makes another appearance, to be used for scintillation detection of alpha particles like the first experiment. Instead of the screen surrounding the gold foil like it is in this diagram, they manually repositioned the screen to where they wanted to detect the deflected alpha particles. It was attached to the end of a microscope which they used to make observations through. By observing the positions of the scintillations, the physicists could determine the angles of deflection.
The physicists wanted to observe the alpha particles being deflected by colliding into the center of atoms. So to maximize the chance of this happening, they used gold for their choice of matter due to its high density and malleability. The more atoms there were, the higher the chance of colliding with the atom particles. But to prevent the entire pencil from being absorbed by the material, it needed to be made into a thin foil, and hence malleable.
A radioactive source, radium bromide, was placed in a lead container. Inside, it underwent radioactive decay. This is when an unstable nucleus tries to become more stable by ejecting out helium nuclei. This spontaneous process produced a stream of alpha particles that was directed towards the gold foil. To minimize the amount of air molecules interfering with the alpha particles, the experiment was performed in an enclosed chamber, which created a vacuum environment. Like what happened in the first experiment, there would be some alpha particles that would be deflected at angles greater than 90 degrees, which was still impossible according to Thomson's model.
In 1911, Rutherford published a paper to share his findings and suggest a change to the atomic model. The results of the experiments could not be explained by Thomson's plum-pudding model, therefore disproving it. He mentions the Japanese physician Nagaoka, who proposed that there was something in the center of the atom in 1904. This was not the end of the developing understanding of the atom, as Rutherford's model of the atom also had its limitations.
This is the scientific model of the atom that scientists accept today. Here's what it looked like 112 years ago. The model of the atom has been transformed over centuries, thanks to numerous scientific discoveries, including the gold foil experiment, establishing the modern atomic model that we all know and see today.